Well, hello class. I thought I'd record this video so that we don't get behind in our material. We're going to cover chapter 24 today. So make sure that you've got the handout from our teacher this morning, and also make sure that you have, let's see, I guess that's all that you need. Also have your calculator out. I have a calculator that I'll be moving over here onto the screen as we need it to show you a few things. And make sure the TV's pulled around there so that everybody gets a good view of the video here. All right, so chapter 24, that's what we're talking about here first. Chapter 24 is when we have data that is not independent, or I should say two groups that are not independent, and we want to see if there is a difference between the two groups. Now, what we did in chapter 23, just to remind you, to give us kind of a baseline of what we're talking about, we were doing comparing two means. And what we had in this case is we had two samples, and the samples themselves were independent. So for example, we started off doing this problem here with two batteries. We wanted to compare to see if the mean runtime for a brand name battery was the same for a generic battery. And so if you look at the samples that we collected, these samples here, these were 6 brand name batteries that we had collected at random. And then we collected, or I should say sampled, 6 generic batteries. There's no connection between that brand battery and that generic battery. They're totally unrelated to one another. They just happen to be in their own respective lists. And in fact, if I had jumbled the order of these brand name batteries or jumbled the order of these generic batteries, it would not have affected our analysis any, because these two across the row here are unrelated. Now in chapter 24, and of course that's one of our independence assumptions, that the two groups are independent from one another. But there are cases where the groups are not independent. And it doesn't really present a problem that they're not independent, but it actually gives us an opportunity to take a look at the individual pairs to see if there's a connection between the two groups. And here's an example, I guess, that we'll start with. But let's start up here. What is paired data? When we did our two-sample t-test, and that was for chapter 23, what we were doing is we were comparing the means of two different. But if the data is not independent, but it's purposely paired or matched, that's going to give us, as I said, an opportunity. So in this example here, consider a study to see if Friday the 13th has an effect on human behavior. And in this example, what we did is we wanted to see if people tend to stay home more on Friday the 13th than on other Fridays. So data was collected that looked at a particular Friday the 13th, and they counted the traffic at a particular highway car counting point. And then they looked at the traffic count on the previous Friday. So they looked here in 1990, they looked at Friday the 6th in July and then Friday the 13th to see if maybe more people were staying home on the 13th. Then they did the same in September of 1991, the 6th and the 13th, and so on for a total of 5 different pairs of data. Now hopefully you see that this is definitely paired data. In other words, we're purposely looking at this particular day, or I should say this particular month, before Friday the 13th and on Friday the 13th. So these two pairs, this one pair of data, they go together with each other. Down here in November, this data point, 117,584, it has to be compared with the 117,263. They go together. If it was not paired, the data would be something like this. I sampled at one point, I sampled a random number of Friday the 13th, and then I sampled a random number of Friday the 6th, and there was no relationship between the two. All right, Now, when we do this, we are not going to use a two-sample t-test like we did with chapter 23, where we compared the means. Instead, what we're going to do is we're going to create our statistic, which is the difference between each one of the data points. So what we're going to do here, this is going to be a one-sample t-test that we're going to run. So we've got a one-sample t-test. On your calculator, that is the t-test function. And we're going to run it on the difference. We're not going to do anything really with the individual data points in the analysis. We're going to create a new one called the difference. If I pull my calculator over here, we need to find the difference then for each one of these. So with your calculator, while I'm doing that, you do the same. So I'm going to take the Friday the 6th minus Friday the 13th for each one of these. I'm going to actually pause the video while I do that. Those are the differences that I came up with. And when we look at this, it sure looks like there was more traffic on Friday the 6th than the following Friday the 13th. In fact, there was more traffic on the 6th than the 13th for each of these pairs of consecutive Fridays. But of course, that doesn't prove or give us evidence that there is a statistically significant difference. Because remember, the reason we're doing these tests, even though we see that, yes, there is a difference, we don't know if our difference is just part of the random sampling variance that we have whenever we draw samples out of a population. Because every time I pull a sample out of a population, I'm going to get a different result. And so there's variance in our sampling. And we want to know, is this the result, this difference that we see? Is it a result of natural variation in our sampling, or is it a statistically significant or rare event? So that's what we're trying to do when we run the test. So we'll do the one sample t-test, but we're just going to do it on this data right here, the difference between those two paired datas. Now, a couple of comments here. You never want to do this kind of analysis when the data are not paired. One of the most common mistakes that students are going to make on the AP test is they're going to see paired data like this. They're going to see that there's the same number of data points. In this case, I've got 5 for each one of these, and they'll assume that it's paired. And you don't want to do that. You have to think about how the data was collected. A lot of times paired data is before and after. You may have a person and you take some sort of measurement about them before something and then after something. So each row is the same person before and after. That's a common way to pair data. This happens to be an observational study, right? We're just observing cars. We're not actually conducting an experiment. We can actually conduct an experiment and purposely pair data together. And that's what we call blocking. And we talked about that last semester. Okay, but either way, we are pairing the data together. All right, let's go to what I think is the next page here. The example that we worked on, as I said, is an observational study. Observational study. And so it's called, what we've done is it's called pairing, or sometimes it's called matching of the data. So each one of the rows goes together. In other words, well, I think it's pretty clear to see that if I had actually jumbled the Friday the 6th data, then my results would be no good, because I need to compare this count of cars with that count of cars, because they happen in the same period that we're looking at. And so what we have to do then, if we're going to run this kind of a test, we have to identify the data as not independent. So the two groups are definitely not independent. They are paired. Each one of the rows is paired. And that means we have to use what we call a paired t-test. But for our purposes, though, what we're going to do for a paired t-test is we're going to run a one sample t-test. And we do that, as I said before, on the difference between each one of the pairs. There is no test, a numerical test or calculator test, to see if two groups are independent or not. We have to know something about how the data was collected to make a determination. If the data is not paired, then we're going to use a two-sample t-test. If the data is paired, like in this example with the car counts, we're going to use a paired t-test, which, as I said, reiterating again, a paired t-test for us is a one-sample t-test on the differences between each pair. As we have done in all of our tests, we have to use some assumptions and conditions. First one, of course, is we have to look at paired data. We have to make sure that the data are actually paired. If the two groups are independent, like in the battery example from chapter 23, then it wouldn't make any sense for us to run this paired t-test. We're going to actually, what we would do in that case is we could take a look at comparing the two means of the groups. All right, so the other assumptions that we also have to look at are independence. And for the paired data, the groups themselves are not independent, but what does have to be independent are the differences in each one of the pairs. So we have to look and say, would it make any sense for there to be any connection between the actual difference, this 1104, would it be connected to any other particular day? And there's no reason to believe that the difference here would be affected by the following pair. So we're taking a look to see and make sure that the difference between the pairs would be independent. And it does have to be independent. We're also looking at, just as we did before in our assumptions and conditions, we are also looking at our 10% rule to make sure that we are not sampling more than 10% of the population. And we also are taking a look at we'll take a look at randomization, right? So we're going to look at the dependence or the paired data. We're going to make sure that the differences are independent. We're going to make sure that we haven't sampled more than 10% of the population. We want the pairs to be randomly selected, and we have to check the nearly normal assumption or nearly normal condition. And in this case, what we are looking at is we would have to consider a histogram of the differences. We are not at all interested in looking at, for paired data, we're not interested in looking at a histogram of the two data sets themselves. That's of no interest. We just want to know, are the differences approximately normally distributed? And it may not be as difficult to check or as strange as you might think it would be, where if my data, the original two data sets could be very non-normally distributed, but the differences very well could be approximately normally distributed. So don't even bother looking at the histogram of the data, just run a histogram of the differences. And I'm going to show you how to do that in the TI-84 here in a second. We are looking to make sure that there's nothing very strange about the differences. We want to see if there's any skewness, if there's any outliers, and if it's unimodal. A lot of times when we've got small sample sizes, like in this case we've only got 6 pairs, the histogram is kind of hard for us to tell whether the larger population of differences would be normal, but at least we'll look at it and make a comment on it. Okay, so we'll do that in this example and see what happens. The first thing we'll look at here will be the how do we run the hypothesis test, and then we'll do the confidence interval. We're going to do this the same way we did the one sample t-test for means. It's just now that our variable of interest is the difference, the differences between each one of the pairs. So our mean, our null hypothesis what we're going to do is we're going to assume the mu sub d. So that's going to be the mean of the differences. We're going to assume it, in most cases, we're just going to assume it to be 0. And then our alternative hypothesis is going to be, those are supposed to be mu's that I'm drawing here. Not coming out too well. With a subscript of d. And these here, our alternative can be not equal to 0, or it could be greater than 0 or less than 0, depending on how the problem is worded. The hypothesis test statistic here is going to be our t statistic with n-1 degrees of freedom. We are going to take the average of the differences minus whatever our null hypothesis is, and in most cases that's going to be 0, and we divide by the standard error of the differences. The degrees of freedom is going to be n-1, where n is the number of pairs, right? Which makes sense because we're really looking at the differences in the pairs. So however many rows there are, how many paired data sets we have, that n-1 of that number is going to be the degrees of freedom. The standard error that we calculate is the same as we did for the means testing. We take our standard deviation of the d, of the differences, and we divide it by the square root of the number of pairs. And then once we do that, then we can come up with our p-value. And as I mentioned earlier, we're going to use the TI-84 t-test to run the test. Now, if we have the individual data, what we'll do is we'll create two lists, L1 and L2, and then we'll make the third list, L3, to be the difference between each one of the L1 and L2 rows. We've done this before, probably last semester when we used our TI-84s in this manner. So let's do that. Run the paired t-test on the Friday the 13th data. All right, what I'm going to do is bring over my calculator. And I'm going to pause this at some point, but I'm going to show you so you can get started on this. So we turn our calculator on. We are going to go to Stat and then Edit. I'm going to clear out my L1 like that. And then I'm going to enter the data in. So in L1, I'm going to enter in the Friday the 6th, and then I'll put in Friday the 13th, the corresponding Friday the 13th in L2. So I'll pause the video here and let you do that. And if the teacher could pause it as well. I think I've got the data entered in here correctly. So there's my L1 representing Friday the 6th. There's L2, the corresponding Friday the 13th. I'm now going to come over here to L3. I'm going to take my cursor up into the header, and then I'm going to type L1 minus L2. So I'm going to do second function L1 minus second function L2 and hit enter. And then it blows in those differences. So those were the same differences that we had calculated manually here just a while ago. And now what I need for this test is I need to get the average difference, and I need to get the standard deviation of the differences. So does anybody know how we're going to get that? Well, what we're going to do is we're going to run one bar stat on L3, and that's going to get us what we need. So I'm going to do stat calc one bar stat. I'm going to change my list to L3. Frequency list should be blank, and then we come down to calculate. There it is. What we need is this 2022. That, excuse me, that is the average difference between the pairs. And we need the standard deviation, which is 1,539.4. Now what we can do, we're always going to look at our assumptions and conditions. I'm not going to spend a lot of time doing it here, but I would be wanting to write a sentence or two on each one of these. I would have to take a look at the paired assumption. I would want to take a look at the independence, make a comment on whether I would expect the differences to be independent. I would comment on the 10% rule. I would comment on whether the pairs were selected at random. And then I would have to consider the nearly normal condition. And that requires us to run the histogram. So pulling the calculator back up, I am going to run the histogram on the L3. I'm going to go into stat plot. Into plot number 1, I will turn that on. I'm going to come over here and hit the histogram. I'm going to tell it to do L3. My frequency should be 1. I hit enter, and then I'm going to do zoom. Oh, let's hit quit here. Let's go back to stat plot. So I'm going to do zoom and then scroll down to zoom stat. Okay, and that's what I get. Now that's not very meaningful. It's only 5 data points, and so there's my histogram. All I can say is, well, it's possible for the data to have come from a normal distribution. I've got a middle point right here. I've got out here on the extreme, I've got it tailing off a little bit. I don't have anything happening over here. I could say it's maybe skewed right, but I've only got 5 data points. So I'm going to make a comment that I did check the histogram, and based on my histogram, I didn't get just one big long middle part. I do have some sort of a distribution. So I'm just going to say, I'm going to be very brief here. It is possible for the differences to be normally distributed. Okay, so we're going to proceed. What we're going to do is we are going to calculate our t-statistic. So what we're going to do is we're going to take d bar minus our mu 0, and we're going to divide by the standard error, which is going to be our standard deviation of the differences divided by the square root of the number of pairs. So this ends up being 2022.4 minus 0, and then we're going to divide this by 1539.4 divided by the square root of 5. All right, pulling our calculator up here. So we'll take, I'm first going to figure out 1539. Let's clear that. So 1539.4, and we'll divide that by the square root of 5. Okay, 688.44. All right, so that's 688.44. Pulling the calculator back up. We'll take 2022.4. I'll divide it by 688.44. That didn't work out right. Let me punch that in again. 2022.4. That didn't work either. Let's try it again. 2022.4. I will divide that by 688.44, and I get a t statistic of 2.94. I can use now for my p-value, since that's really what we need for our hypothesis test, what we are looking at here, just tying this back to a t curve. So this is our t distribution. We have 2.94 out here. This is a two-tailed test, right? So I've got minus 2.94 out here as well. And we're looking for the area that's on these two tails. Right here in the middle, that's going to be our average difference between the pairs. So I need to find, for my p-value, I need to take 2 times, and I'm going to use inverse t. And what I need to do for the inverse t is I need to give it, and actually we're not going to use inverse t. That's if I needed to find a t-score, but we're going to use t-CDF. That's how we're going to find the area under a t-distribution curve. So we're going to do t-CDF. We have to give it a lower value, so we're going to go 2.94 to infinity. And we have to give it the degrees of freedom. The degrees of freedom are n minus 1, which is 4 in this case. I've got 5 pairs, 5 minus 1 is 4. And I'm doing the 2 multiplication because since it's a two-tailed test, right, this tcdf command is going to give me this area right here. I need to also combine it with this area. And this area over on the left is going to be that area, same as that area on the right, so we just simply do a 2 multiplier. Well, let's pull the calculator back up. Let's go into, we'll go into stat, second function distribution, and we come down to tcdf. Our lower is going to be 2.94. My upper will do infinity. And then the degrees of freedom, 4. We paste that, we execute it, and there we have 0.0211. But I have to multiply that by 2, and I get 0.04 and some change, I believe. But it's approximately 0.04 is my p-value. No alpha or significance level is specified in the problem, so we're going to say that my alpha is 0.05. And at this point, I'm going to make a comment on the fact that my p-value is low, and I have evidence then to reject the null hypothesis, and that I have detected that there is a difference between behavior on Friday the 6th and Friday the 13th. And I would write that out in sentence form. Okay, so that is the hypothesis. Now, if we wanted to run this, if we wanted to run the t-test, right, we did this all manually, but if we go back to our calculator, we could run, if we go to stat and test, there is a t-test. So we could run that. And I've got data in my L3. Remember, we're just testing the difference in the pairs. So I'm going to use data. My null hypothesis is 0. The list is going to be second function L3. Frequency is 1. It's a two-tailed test. And we're going to calculate. And there it is. There's my p-value, 0.042, which is what we had gotten manually. So you can always run a one-sample t-test in about 30 seconds. But on our free response questions, we are going to be showing our work like this. Now, how do we do the confidence interval? Well, it's pretty much the same thing. Let's see here. So for a confidence interval, this is what we're going to do. We're going to come up with our t-statistic with n minus 1 degrees of freedom. And actually, this is not our t-statistic. It's what we call our critical value. For the z-test, we know for a 95% confidence interval, it's always 1.96. But when we're doing means testing, this critical value is dependent upon the sample size. So that's why this is not going to be just a fixed value for a given confidence, for a particular confidence level. It's going to change depending on the sample size. But we'll take our average in the differences in the pairs, plus or minus whatever our critical value is, which we'll find using our inverse t command, and then we'll multiply that by the standard deviation. So this is our margin of error. So the pattern is always the same on these confidence intervals. It is our best guess as to what the statistic is, plus or minus some margin of error. And here is our standard error that we're calculating for the difference in the pairs. Okay, and like I said, we're going to use our inverse t function to get our critical value t star. To execute the test and obtain the interval, we can use t interval, I believe is what the command is. But we're going to do this manually. Here's an example that we're going to use to try this out. What we want to do is find the confidence interval for the differences between mean high temperatures of these European cities. I want to examine the histogram, and we'll take a look at the box plot as well to see if it meets the nearly normal condition. So what we want to do here is we're going to put in L1 and L2, and then in L3, since it looks like July is larger than January, I like to stay with positive numbers. I'm going to take L2 minus L1 and create that in L3. So what our teacher can do at this point is pause the video, and I want you to use your TI-84 and put that data into L1 and L2 and create L3. So we'll give you about 5 minutes to do that. I think I've got my data entered in correctly. I've got my L1, L2. There's L3, the difference between the high temperature and low temperature for each respective city. We still have to go through our assumptions and conditions. So I'll run through these pretty fast. We have to comment on the fact that why we think the data is paired. And obviously I've got one city, I've got 2 data points, one in January, one in July. So it makes sense for me to be comparing 34 and 75 because that goes with one particular city, Vienna, and so on and so forth. I have no reason to believe that the differences are going to be related to one another, so I assume independence between the differences. This sample is, I'm going to guess that this is less than 10% of all of the European cities that there are. Pretty safe assumption. I'm going to assume that these are random cities that were chosen. And I have to look at the nearly normal condition for the differences. I'm going to pull my calculator back up here, and I'm going to run the histogram on L3. So we'll go into stat plot. I've already got it set up, it looks like, for a stat plot histogram on L3. I will then hit zoom and zoom. Oops, didn't want to do that. There we go, and zoom stat. Okay, so there it is. Well, maybe we've got a bit of skewness to the right because I have a data point out here, it looks like. But, you know, that's not too bad. I could envision, if I had more samples, that this could fit a normal distribution. You know, I don't have absolute proof or certainty that these differences are normally distributed, but, you know, as a statistician, we're looking to have a valid reason to proceed in our analysis. I don't see anything here that would lead me to not want to analyze this as a normal distribution. We could go back and look at the box plot. So we'll give that a try. We're going to look at this graph right here, and I will try doing a zoom stat on this, see what happens. Looks like we have an outlier here. That point would represent an outlier. If we go back and look at the data, does it look like there is an outlier here? Perhaps the 55 difference is an outlier, or maybe the 22, but let's go back. Second function stat plot. We'll do zoom. And there it is. But I'm going to proceed. In my results, I can make a comment that I did have an outlier in my differences. I could choose maybe to throw out that data point, but I'm just going to proceed and note what I saw, that that it is unimodal, maybe some slight skewness, and there seems to be an outlier. Probably not an extreme outlier, but there is an outlier. All right, so we'll go ahead and analyze our data. So we've done our assumptions and conditions. Our confidence interval is going to be the average differences, the average in the differences in the pairs, plus or minus t star with n minus 1 degrees of freedom, multiplied by the standard error of our differences. Going back to the calculator, I need to run 1var stat. So I'm going to do stat calc 1var stat, and I'm going to do it on L3, which is the differences in the temperatures. Frequency list is blank, calculate, and that's what I need. I've got 36.8, so dvar is 36.8 degrees. And then we need our standard deviation, which is the SX right here. That's going to be 8.66. We do need to get our critical value with how many degrees of freedom. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 11 degrees of freedom. And that's going to be found by using inverse normal. Inverse t, I should say. So used to using inverse normal. So we're going to use inverse t command. We're going to assume it's a 95% confidence interval, so we're going to say an area of 0.975, comma 11. So I will pull up the calculator, and I will do let's see, second function, and let's quit. Okay, so there's my inverse t. Oh, sorry about that. All right, so the area will be 0.975. Degrees of freedom is 11. Paste it in. What do we get? 2.2. So I've got 36. So here's my confidence interval. It's going to be 36.8 plus or minus 2.2 times, and then our standard error is going to be 8.66 divided by the square root of 12. Okay, so doing that on the calculator. So I'll do the margin of error first, 2.2 times 8.66 divided by the square root of 12, 5.5 it looks like. So I've got 36.8 plus or minus 5.5, so that's going to give me a confidence interval of 31.3, comma, and if I add this up right, it's probably going to be 42.3. So I am 95% confident that the difference between the cities, between the January and July temperatures, is somewhere between 31.3 and 42.3 degrees. So there we go. And that's it. So I would make a comment on that about my confidence of 95% being that the difference between the city temperatures January and July is that particular range. Okay, well, I hope that was helpful. What I want you to do now in your textbook, I want you to work problems 28 and 29. That's going to be an in-class assignment for you to do and hand in to the teacher. You can work in pairs quietly, but you do need to hand in, everyone needs to hand in those two problems finished completely. Make sure you do your assumptions and conditions for each problem and show me all of your work. And then your homework assignments, your homework assignment that will be due on Thursday is numbers 32 and 33 in chapter 24. And I will collect that. Okay, and also if the substitute would also collect the homework that is due for today, which is your chapter 23 problems 18, 37, and 38. If you could hand those in today too, I would appreciate it. Okay, class, thanks. I will see you all on Thursday.